Ja, dat mag jij zeker. I'd like to invite Evelien Volke, who is associate professor at Kent University in the field of biosystems control, and she's also the secretary of the IWA Specialist Group on Instrumentation Control and Automation. The floor is yours.
Thank you. It's already getting dark outside and it's quite cozy here with the chandeliers, but I still will try to keep your attention for another 20 minutes with a presentation dealing with modeling and control of granular sludge reactors for autotrophic nitrogen removal. I will start with an introduction. I will briefly introduce the autotrophic granular sludge reactor model we have used in our studies, and then we will examine what the reactor behavior is like. From that, we will look what are the implications for modeling, and I will end with some conclusions. Okay, granular sludge reactors are in fact biofilm reactors in which the biomass grows as dense and fast settling granules. They have a large biofilm surface area compared to flat biofilms because they are spherical, but there is no carrier material. This allows to have a high biomass concentration in the reactor and as a result have very compact systems with a high loading rate. These granular sludge reactors can be used for wastewater treatment. We know them, of course, from anaerobic granules, but this is not what we're going to discuss today. We're looking at reactors in which there is at least a part, there is some aeration. This can be for simultaneous removal of COD, nitrogen, and phosphorus, or for partial nitritation NMOX. And this results in a small footprint, as you can see from this picture. So this is an example of a wastewater treatment plant in Olburgen, the Netherlands. And here you see the area needed to treat 90,000 people equivalents, while this small area, and I have to say it's combined with the part here, is what we need to treat 40,000 people equivalents. So it's quite compact if you compare them. Now, what is partial nitritation NMOX? Because today we're going to discuss on granular sludge reactors for partial nitritation NMOX. Well, first recall what is conventional nitrogen removal from wastewater. This happens through nitrification and denitrification. This we all know. So ammonium is oxidized with oxygen to nitrite and subsequently to nitrate and then back to nitrogen gas by adding a carbon source. Now, in partial nitritation, first nitritation, we oxidize ammonium to nitrite only and we prevent further nitrate accumulation. And then there is a combination possible with an NMOX process. For that we only oxidize half of the ammonium, and then that's why we call it partial nitritation. And then this 50% ammonium, 50% nitrite mixture can be converted simultaneously to nitrogen gas by NMOX bacteria, which are autotrophic and as a result do not consume any organic carbon source, and as an additional plus do not emit any CO2. So when we compare partial nitritation NMOX processes with conventional nitrogen removal, they will consume up to 63% less oxygen, up to 100% less carbon source, also less CO2 emissions, almost no CO2 emissions, also less sludge production compared to conventional nitrification, denitrification. When we are working with granular sludge reactors, it's possible to achieve partial nitritation and NMOX in one reactor. So we only have one reactor in which ammonium is converted to nitrogen gas, and our control objective is, of course, to achieve the maximum conversion possible of ammonium to nitrogen gas. We have modeled this type of system, and for that we have used a one-dimensional biofilm model, which means that we only consider radial gradients. So, the sphere. It was implemented in the Aquasim software, which is used quite often for one-dimensional biofilm modeling. And we considered oxidation of ammonium, of nitrite, and then the NMOX conversion. So we considered three groups of bacteria: AOB, NOB, and NMOX bacteria. We have also added processes for decay. It was through the endogenous respiration mechanism for all bacterial groups. We neglected heterotrophic growth, and this was a reasonable assumption given that we assumed that there was no COD present in the influent, only ammonium. There was a given influent flow rate and then some conditions for the reactor, temperature 30 degrees, oxygen at a constant level, that's quite important, but we have then varied the oxygen level. The reactor volume was 400 cubic meter, of which at steady state 100 cubic meter was taken up by biomass. Now, what were the results? So how does this reactor behave? In order to understand this, we first need to know what happens in such a reactor. Well, in fact, we have quite some competition there. We have competition between AOB, NOB and Anammox bacteria for space in the granule, because space is limited there, and also for substrates. If we look, AOB and NOB are competing for oxygen. Then we have the AOB and Anammox bacteria competing for ammonium, and NOB and Anammox competing for nitrite. So there's a lot of competition there. Now it's clear that the presence of AOB is required for the survival of one of the other two groups. So AOB will always be present because they need to produce nitrite, which is needed by the two other bacteria. Now whether NOB or Anammox bacteria will win the competition will depend on the oxygen concentration in the reactor. And this is what we clearly showed with the following simulations here. So what you see here, I will show a lot of slides like this, so maybe we better have a look at it in detail. So each dot is the outcome of a steady state simulation. You see here the concentrations of all nitrogen compounds in function of the bulk liquid oxygen concentration. And then here you see the corresponding biomass fractions in the granules. So for each oxygen concentration, you have a certain steady state biomass fraction and you have a steady state reactor performance. These fractions, so it was a one-dimensional model and the fractions were calculated by integrating the biomass profiles within the granules. We see that at low oxygen concentrations, Anammox bacteria are present and we have nitrogen gas formation. So indeed, Anammox bacteria, here in red, they are present at low oxygen concentrations, and we have nitrogen gas formation corresponding with that. At higher oxygen concentrations, we have the NOB present, in blue, and there is nitrate formation. They produce nitrate. If we have too low oxygen concentrations, this will lead to incomplete ammonium conversion, so that's not interesting. So there is in fact a nitrogen peak, so there is an optimum oxygen range to have an Anammox conversion. There was some color animation on this, but it's not visible with this resolution, I'm afraid. These conclusions are similar to what has been obtained previously for flat biofilms by other authors. So we see that oxygen is a control handle for autotrophic nitrogen removal in granular sludge reactors. This is nice, but we already knew that. We already knew this from flat biofilms. So let's tell something new. We have seen there is also an influence of the granule size. We have performed first simulations for a uniform granule size, meaning that all the granules in the reactor were assumed to have the same size, so the same diameter. And here you see the steady state nitrogen concentrations in function of the particle diameter, and the same biomass fractions also in terms of the particle diameter, now for a fixed oxygen concentration in the bulk. And we see that if the granules are small, we have nitrate production, red line here, and NOB are present. If we have larger granules, Anammox bacteria will win the competition. Anammox bacteria are growing, and we see that we have nitrogen gas production. That's too fast. For intermediate sized granules, we have nitrite accumulation. This also agrees with experimental findings from other research groups. Now, how can we explain this effect of the granule size? Well, as the granule size increases, the surface to volume ratio decreases. And that means that we have a higher surface load. As a result, the oxygen penetration depth will decrease, and we have a larger anoxic to aerobic volume fraction. And that is why in smaller granules, so we have the nitrate production, while in the large granules, Anamox will win the competition. So large granules are favorable for Anamox conversion. Now, in reality, we will not have just one granule size in a reactor. We will have a distribution. For instance, distribution like this. We have used some experimental data of Vlaming et al., where 4 different granule size classes were distinguished, each having a certain relative abundance in terms of percentage of VSS of each granule size class. We have also modeled this and assumed a model with 4 different size classes in Aquasim. Now, that was quite a challenge, I have to say. We didn't expect this on beforehand, but so we found that what you need to do, of course, is to take a number of classes equal to a number of biofilm compartments. People, I don't know if there are any people working with Aquasim here. So all small granules for different compartments. And then, of course, you need to interchange the bulk liquid, because in reality, all of these are in the same reactor. So we've connected an additional bulk liquid compartment to that. And there should be sufficient mixing between all compartments to have the same bulk composition in all compartments. We've encountered quite some numerical instabilities, and it was really a numerical problem. This was verified very rigorously. And finally, we were able to solve them by using this configuration and by taking the same bulk liquid volume for all the biofilm reactor compartments and by dividing the influent flow over the compartments. This is not something which I plan to do very often. Here is the result. So now we see the steady state composition for each granule size. So this is now an intersection of the granule. 0 means the center of the granule, and in this case 0.06 something is the outside of the granule. And here you see the fractions, the profiles of all the bacterial groups. You see, for instance, that the AOB, the ammonium oxidizers, are present at the outside of the granule, where they have easy access to oxygen and ammonium present in the bulk liquid. Then you can have some NOB present just underneath, because the NOB still need oxygen, and they also use the nitrite produced by the AOB. And then you may have Anamox bacteria, more towards the center, and then more at the inside, the inert material originating from biomass decay will accumulate. Now, here you see a profile just for the smallest granules, but I've just said we considered 4 different classes. So we have 4 different profiles within the same reactor. And you see that as the particle size increases, because well, this is the smallest and this is the larger particle size class, the amount of inert material also increases. So the fraction of inert material in the particles increases as the granule size increases. NOB, so nitrite oxidizing bacteria, are only present in the smallest granules. And this is also in agreement with experimental findings by Marie Winkler et al., who has also studied bacterial compositions within a single granular sludge reactor. Now, what are the implications of all this for modeling? Well, how should we model a granular sludge reactor? This now, I take these conclusions for partial nitridation Anamox, but maybe some of that could also hold for anaerobic digestion models, for instance. One could incorporate the granule size distribution in the model. This is the most complicated. It means that you have multiple granule size classes in one model. It's the most complicated, but it's also expected to give the most realistic results. It should. And you should represent each particle size class by a characteristic diameter. We cannot have an infinite number of classes, so we need to discretize this. And for each class, we will represent them by a characteristic diameter. And that's another problem, because which characteristic diameters should I choose? Should I choose the arithmetic mean, or the surface weight mean, or the volumetric mean? The surface weight mean, for instance, is the characteristic diameter for which the surface of the corresponding granule size will be the same as the mean surface of the class you consider. Now, then there was also an alternative approach. We have also examined a class weight approach, in which we indeed consider, for instance, 4 different classes. We represent each class by a characteristic diameter, but we do the, in fact, we make 4 different simulations, each with a single granule size. So it's a uniform distribution, but we make 4 different simulations with 4 different uniform distributions, and then you just weigh the results for the different classes according to the relative abundance of each class. Yeah, that's perfect. But in this way, what you do is, in fact, you neglect the interaction between particles of different sizes. And then you can just assume a uniform granule size. This is the most simple. You represent the overall distribution by a single characteristic diameter, which can again be the arithmetic mean, surface weight mean, or volumetric mean. But in that fact, then you really neglect the distribution. Now, these different modeling approaches, this was 3 different modeling approaches, each with 3 different characteristic diameters, so 9 different simulations. Well, the simulation results are very different, as you see here. There are quite some variations in the amount of nitrite, nitrate, and nitrogen gas formed, predicted by the model, and these differences are due to the chosen modeling approach and the chosen characteristic diameter. So which modeling approach should I choose? Well, my advice is you just use a uniform granule size. It's the simplest, and it's good in case only the overall reactor behavior needs to be assessed. Why choosing this one? Because it's the most simple one, and you need the least amount of experimental data. And the effect of inaccurate granule size distribution modeling can, in my opinion, be compensated during the calibration of other model parameters. Or, what you can also do, choose the most complicated, incorporate the granule size distribution. That only in case you want to study the solute exchange between particles of different sizes. Now, what you should not do is use the class weight approach. Do not make different simulations and then weigh the results. It's not a good modeling option because the interaction between particles cannot be neglected. That was shown here. And which characteristic diameter should we choose? Well, choose the surface area weight mean diameter because this governs the exchange of substrates, or choose the volume weight mean diameter because this determines the amount of biomass you have in your system. Do not use the arithmetic mean because this doesn't have a physical meaning. But what you have to do, you have to mention which one you use, because often that is a problem in current research articles. So conclusions: autotrophic nitrogen removal through partial nitration NMOX in a granular sludge reactor is significantly affected by the granule size and its distribution. The NMOX conversion is favored in relatively large granules. Small granules tend to accumulate nitrite or nitrate. In a single granular sludge reactor, NOB are present in the smallest granules and NMOX are present in larger granules, and there is interaction between granules of different sizes. The way in which the granule size distribution is described will influence the simulation results, so it's important to mention which approach you have taken. We have also shown some limitations of the Aquasim software, which is often used, but is very limited to model detailed granule size distributions. Thank you for your attention.
And thank you for keeping in time. There's some time for 1 or 2 questions before we can leave this beautiful building and go to the conference dinner. Question?
Yeah, Klaus-André Siemens, Water Technologies. You brought a whole new level of understanding of what is happening on the granular size, or within the flux, if you want so. Is there any chance at all at the horizon to actively influence the granular size? So to kind of use that knowledge and have it as a toolbox to actively influence the performance of the reactor by means of having whatever actor available to fine-tune the granular size?
Thank you for this question. Yeah, indeed, there are some possibilities to use what we have seen. For instance, we've seen that NMOX conversion is favored in large granules. So what you would may want to have is you want to wash out the smaller granules. Now it's the case. It has been found that in fact the smallest granules are mostly at the top, and the largest one are typically at the bottom. So what one can do is selective sludge withdrawal. So to remove, for instance, the small granules from the top, and also maybe you want to remove some particles which become too large from the bottom because they have more inert material. This is something which has been proposed by Winkler et al., by the way. Before, well, it was independent research, the simulations and then the experiments, and it was nice that it coincided so well.
Very clear answer. One final question. Oh, there's two people. We do two final questions. First Henry and then you.
Thank you, Evelyn, for this nice presentation. I like the emphasis on the granular size. That has not much been done so far. But this last question about the influencing the size, you can, of course, also manipulate the shear forces in order to obtain a certain granular size. But my question, you showed the influence of the bulk DO concentration and the dissolved oxygen concentration. And in fact, well, the dissolved oxygen concentration, the dissolved oxygen will penetrate partially in the granule. And but you didn't show profiles of oxygen in the granules. But that could demonstrate, I think, how it would work. Because, or maybe I missed it.
But you're right, I didn't show the profiles, but sorry, this is going quite slowly. Yeah, I did show the oxygen penetration depth here. So what you see here is how much millimeters the oxygen penetrates into the granules. So,
yeah. And in that case, but because this is for one particle, yeah, one granule.
No, this is for different granules. So if you have a particle of 1 millimeter,
okay.
the oxygen penetration depth will be 0.06 millimeters. If you have a particle of 2 millimeters, the oxygen penetration.
Okay, yeah, that's clear. Yeah. Yeah.
Maybe was a bit too fast.
And the final question.
Yes, thank you. Paula Lindell from Helsinki Region Environmental Services Authority. I have a question. How did you control the retention times of the bacteria? Because the AOPs and Anamox have very different optimum retention time.
It's okay. So how did I control the retention time? In a model, this is very simple. I just assumed a fixed granule size, and the granules stayed in the reactor because I didn't have any problems with sludge washout. So what I did, so the artificial thing, and maybe that's what you are referring to, is that the granule size was assumed constant. So what it did is mathematically I made sure that the detachment rate was equal to the attachment rate once the granule had reached its full size, and in that way you have you automatically get the SRT. I didn't calculate the SRT. You could calculate it if you want by looking how much biomass actually leaves the system with the effluent. Yeah.
Thank you. I just heard from the organization that we had to be strict on time because tonight's program we're not supposed to miss. So I'd like to thank you and all the other speakers for your good presentations. And I'd like to thank the audience for interaction and having questions ready. I had a list of questions, but they weren't necessary. And I'd like to remind you that at 6:15 we leave at the outside here at the door as a group towards the boat for the conference dinner. So enjoy this evening.